Okay, let's look at these matric past paper questions on electrostatics. These are all from November and June and February, March electrostatics questions in past papers. So it says to you, two charges of +2 nanocoulombs and -2 nanocoulombs are located on a straight line. S and T are 2 points which lie on the straight line as shown in the diagram below. Well, it's not quite exactly where T is, but we can fix that. Which one of the following correctly represents the directions of the resultant electrical fields at S and T? Now remember, it says to you electrical field, and the definition of field says which way would a positive point charge move. So if I put a positive point charge at S, it would be attracted this way, okay, by the negative 2 nanocoulomb on the right, and the positive 2 nanocoulomb on the left would repel it that way. So this one would move to the right, and then T, if I placed a positive point charge, because whenever we talk about field, we talk about positive point charges. If I put a positive point charge at T, it is positive. This one over here is negative, so it will want to move to the left. So the direction of the resultant electrical field at S will be to the right, and at T to the left. So the answer is A. So the next question is, two charged spheres of magnitudes 2Q, I always recommend drawing a picture, and Q are placed a distance R apart on insulating stands. If the sphere of charge Q experiences a force F to the east, then sphere charge 2Q will experience a force. Okay, this question is testing you on your understanding of Newton's third law as it relates to electrostatics. So according to Newton's third law, the force exerted by the one sphere on the other sphere is equal in magnitude and opposite in direction. So it's not interested in the charges here, okay? You can see that the one charge is 2Q and the other charge is Q. But if we do the equation for this, F equals K Q1 Q2 over R squared, the final force is a single value, and it doesn't matter if we're looking at 2Q or Q, the force is a single value, but the force is always in equal and opposite directions. So it will be the force F. Okay, so these two are definitely not okay because the forces can't get bigger unless you change the charges or change the distance. So it has to be force F to the west, so the answer is A. Then it says to you the next one, two charges plus Q, that's plus Q over here, and minus Q are placed a distance D from a negative charge minus little q. The charges plus Q and minus Q are located along lines that are perpendicular to each other as shown in the diagram below. Now it says to you, which one of the following arrows correctly shows the direction of the net force acting on charge negative Q due to the presences of plus Q and minus Q? So to find the net force, we have to find the individual forces and then find the resultant. So if we look at little q and we look at this positive q over here, what will little q want to do? Little q is negative, that big Q is positive. Little q is going to want to move towards big Q, okay? And then it says to you, I've got negative big Q and negative little q. What will little q want to do? Little q will want to move to the left. You realize little q doesn't want to do anything because it doesn't have emotions, but I like to think of it in those terms. So like charges repel, little q will be repelled to the left. So if we look at those two arrows, I've got one arrow going up and one arrow going left. If I make a vector triangle out of them, I will end up with the resultant force going up and to the left. And so up and to the left in all of these things, this will give me the answer of C, up and to the left. Okay, 1.4. Two identical light graphite covered spheres, P1 and P2, are suspended using identical thin insulated threads. P1 is charged, but P2 is neutral. The spheres are then brought into contact with each other as shown in diagram 1. That's this one over here. Thereafter, the spheres assume the positions as shown in diagram 2. Which one of the following statements concerning the charges on the spheres possibly explains why the spheres move apart after touching, as shown in diagram 2? Well, this relies on the law of conservation of charge, which they start teaching you from grade 10. In an isolated system, the net charge is conserved during any physical process. So when we have P1 plus P2 and we touch them and we bring them apart, they will have a new charge that is equal, okay? And so then the charge is equal, and when it is equal, it means the sign of the charge is the same, okay? So if for instance P1 was positive, after they're touching, both spheres will be positive. If P1 was negative, after they're touching, both spheres will be negative, because that's what the law of conservation of charge tells you, that basically the charge is shared or averaged out during any physical process. So obviously they are repelling because the charges are the same. The sign of the charge and the magnitude of the charge is the same. So we're going to immediately rub out C, because C has got a plus and a minus on it, okay? So we can't have that after they charge. That leaves me with three possibilities, okay? A, B, and D. The correct answer is D, because in any system, the net charge is conserved. The charge will be equal in all ways, in magnitude and in whether it's positive or negative. So the answer is D. Okay, now 1.5. Three charged spheres, X, Y, and Z, supported by insulating threads of equal length, hang from a beam as shown in the diagram below. Sphere X, the one in the middle, is negatively charged. Sphere X attracts sphere Y, which means sphere Y is going that way, but repels sphere Z, so sphere Z is also going that way. All right, so like charges repel. So this tells me like charges repel. If X is negative, then Z is also negative. So we're going to rub out anything that tells you Z is positively charged. Okay, why am I not dealing with the other one first? I'm not dealing with the other one first because remember that attraction can occur between a positive object and a neutral object, Attraction can occur between unlike charges and between a charged object and a neutral object. So I can only in the beginning conclusively state that Z is negatively charged. And then if I look at my other answers, Y must be positive because it is being attracted. There are no neutral options in my answers. So the answer is A. Okay, if we look at 1.6, two identical spheres R and S on insulated stands carry charges of plus Q and minus Q. So now when they do this, plus Q and minus Q, if we're using little q for both of them, with these charges, the magnitude or the size of the charge is identical, okay, but the sign is different. Now it says to you, sphere R exerts an electrostatic force of magnitude F on sphere S. It says the two spheres are now brought into contact and returned to their original positions. Now, at the moment you bring something into contact and separate it, you use that formula about Q nu equals Q1 plus Q2 over 2, okay, which is the law of conservation of charge. In an isolated system, the net charge is conserved during any physical process. So if we look at plus Q and minus Q, and we look at this like algebra, this is plus 1Q, and this is minus 1Q. So plus 1 minus 1 gives you 0, okay? These two spheres, when they touch, they are going to neutralize each other because they've got exactly, the one has got exactly the same number of electrons gained and the other one's got exactly the same number of electrons lost. So R lost electrons, S gained electrons, but they lost and gained the same number because the charge is the same. So plus Q minus Q gives you 0. If there is no charge, there can be no force. So the answer here is A. Now it says to you, the magnitude of the electrical field at a point P from a positive point charge. So if I've got the point charge here, and I've got the point P over here, they said to you the electric field, remember the electric field is given the symbol E, E equals X newtons per coulomb, okay? Which one of the following statements below regarding this electrical field is correct? So now we want to have a look here. We want to look at this formula E equals F over Q, okay? Remember the field is the force per unit charge, and the direction of the field is which way will a positive point charge move. So it says to you the magnitude of the electrical field at point P from a positive point charge is this. So this is a positive point charge, okay? So if this was a positive point charge and we drew the field lines show which way a positively charged object would move. So positively charged objects are going to move away from another positively charged object. So the field at P, if I put a 1 coulomb charge here, the field will be going away, okay? So we want an answer with a directed away. So we're going to remove these answers because the field shows which way a positive charge would move, and a positive charge is going to move away from another positive charge, okay? Then it says to you the field is the force per coulomb. So if we want the force per coulomb, and it says that this is X equals the force per coulomb, the only way for this to be correct is if the charge is 1 coulomb, because if we divide that by 2, it is going to the charge 2 in number B. It says the force on a 2 coulomb charge. If E equals F over Q, if we divide the force by 2, it is not going to have the same magnitude. So the answer is A. It helps with this one if you know your definition of what is electrical field at a point. An electrical field at a point talks about what would happen to a 1 coulomb charge placed at that point, and a 1 coulomb positive charge. Okay, now we've got a similar question to the one that came before. It says 3 identical positive point charges. They are all positive. If they are all positive, they are all going to repel, like charges repel. Okay, so it says to you they're initially situated on a smooth flat table at the corners of a right angled triangle. The diagram below shows the charges as viewed from above. So there's Q1, Q2, and Q3. They're corners of a right angled triangle. Which one of the following diagrams shows the direction in which Q2, that's this one at the corner, will move as a result of the electrostatic forces exerted by Q1 and Q3 on it? Well, if we look at Q2 and we look at Q1, the charges are the same. Q2 will be repelled, so Q2 will move off in that direction. If we look at Q2 with respect to Q3, the charges are the same. They will be repelled. It will move off in that direction. So I have one charge to the left, one force to the left, one force down. So if I draw in my vector triangle, the resultant will be down and to the left. So 1.8, the answer is C, down and to the left. Now 1.9, two small identical metal spheres, each carrying a charge Q, are brought into contact and separated. So I've got Q over here, and I've got Q over here, and then I bring them together and separate. What will the charge on each sphere now be? So the law of conservation of charge tells you in an isolated system, the charge is conserved. So the formula goes to find the average, basically Q1 plus Q2 over 2. So if I go Q plus Q, I get 2Q divided by 2. I will still have Q on both of the spheres, if you put it in the formula. And also if you apply logic, if we had equal charges before, we will have equal charges after. So the answer is C. Now this one's about field again. The magnitude of an electrical field, remember field is given the symbol E, at a distance R, so I've got a point charge and I've got this distance R, okay. The magnitude of an electrical field at a distance from a point charge is E. The magnitude of an electric field at a distance to R will be, so let's have a think about this one. Remember as well, E equals F over Q, but E is also equal to KQ over R squared. So we have doubled the distance. Okay, so in here we're going to put in the denominator 2R and square it. We have not changed Coulomb's constant, and we've not changed the charge. Okay, so we will then end up with a quarter of the field. Remember, this is an inverse square law. The force decreases. If we look at E equals F over Q, the force decreases with increasing distance. So the bigger the distance, the smaller the force, and also the smaller the field. So 2 squared is 4, so it is going to be a quarter E. Now PQ and R, this is 1.11, PQ and R are 3 charged spheres. So P, I always like to draw a diagram, Q, R. When P and Q are brought next to each other, they are attracted to each other. When Q and R are brought next to each other, they repel each other. Okay, so what do we know if we are repelling each other? These two have to have the same charge, like as in the same charge, not the value, but as in the same, they are both positive or they are both negative. Okay, now P and Q can be attracted if P is neutral and Q is charged, but they said P has got a charge. So this one, P and Q must have opposite charges. So if Q and R are the same and P and Q are opposite, how will P and R be? Can P and R have the same sign? No. P and R have opposite signs. This looks promising. Yes. B looks promising. P, Q, and R have the same sign. No, that's not possible because we have got some attraction going on. P, Q, and R have equal charges. No, if we have equal charges, they will all repel. So the answer here is B. Okay, now we've got 2 charged particles placed a distance r apart. The electrostatic force exerted by one charged particle on the other is F sub E. Which one of the graphs correctly shows the relationship between the electrostatic force and the square of the distance between the 2 charges? Well, if we have a look, okay, the formula says F equals K Q1 q2 over r squared. So the relationship between F and r squared, F is inversely proportional to r squared. So if F is big, okay, to get a big force, we need a small r squared. The bigger the distance, the smaller the force. The bigger the force, the smaller the distance. So we can't use this one because it is an increasing curve, okay? And we can't use this one because it's constant. It will not be constant, okay? So we're left with these two decreasing curves. But if we plot FE against r squared, we are going to end up with this curve like this, which is answer B. Okay, 1.13. The magnitude of the electrostatic force on a charge Q1 due to another charge Q2 is F. Both the charges are now doubled without changing the distance between them. Remember, we've got that formula up there, F equals K Q1 Q2 over R squared. So if we double the top of it, we are going to double, if we double the right hand side, we are going to double the left hand side. Look, F equals K Q1 Q2 over R squared. What will happen to the force if Q1 becomes 2Q and Q2 becomes 2Q? Then 2 times 2 is 4. We will increase the force, and so the new force will be 2 times 2, 4F, because we have not changed the distance. If we change the distance, if the distance got bigger, the force would get smaller. If we increase the distance, the force gets smaller. If we decrease the distance, the force gets bigger. But we never changed it, so we only need the magnitude of the charges. Okay, we nearly finished here. We've got 14, 15, and 16 to go. It says to you, 2 small identical metal spheres on insulated stands carry charge of negative Q and positive 3Q respectively. When the centers of the spheres are a distance d apart, the spheres experience an electrostatic force of magnitude F on each other. So in the first situation, we have F equals K Q1 Q2 over R squared, and here the forces are Q and 3Q, okay? So it's Q times 3Q. Now it says too, the spheres are made to touch. If the spheres touch, the law of conservation of charge applies, and we get Q nu equals Q1 plus Q2 over 2, and I have negative 1 plus 3 over 2. Negative 1 plus 3 is positive 2 divided by 2. They are each equal, now going to have 1Q on each other. Okay, remember that these were minus 1 plus 3Q. And so it's just like algebra. So we have 1Q now, and they are back in the same position, so R has not changed. So what is my new force going to be? K Q1 Q2 over R squared. What have I now got? I've got 1Q times 1Q, which gives me Q squared. So this is 3Q squared. This is 1Q squared. So how has the force changed? The force has decreased. So any answer that is bigger, okay, we are going to immediately do away with. This one is bigger than F. This one is bigger than F. We're going to get rid of them because the force has decreased. So the answer, if we compare them, this force was 3Q squared. This force is 1Q squared. This one is 3 times smaller. So 3 times smaller is the same as saying 1/3. So the answer here is B. The new force is 1/3 of the original force. Now we've got particle P has a charge of Q, and particle R has a charge of 2Q. They are separated by a small distance R. Which one of the following statements below about the electrostatic forces, the force PR, which is P exerts on R, and the force RP, which R exerts on P, is correct? This is once again testing you on your knowledge of Newton's third law. This has got nothing to do with the charge on these two, okay? Remember to calculate the force. We go F equals K Q1 Q2 over R squared. So if we're calculating the force, we will get a single value for the force, and the force will be equal and opposite on both of these spheres regardless of their charge, okay? So the two must be equal, but they are in opposite directions. Force is a vector. If the forces are in opposite directions, they will have opposite signs. So if this way is positive, this way is negative. So the first one is wrong because the forces are equal. The third one is wrong because the forces are equal. So if we pick between B and D, the answer is D, because the forces, according to Newton's third law, have the same magnitude but are in opposite directions. So the force of P on R is equal to minus the force of R on P. And the last question, which is from November 2020, it says two identical metal spheres, P and R, on isolated stands carry different charges. The charges are brought into contact and separated again. This is the law of conservation of charge. The net charge in an isolated system remains constant. If the charge on sphere R after separation is Q, the charge on sphere P after separation is, this is too easy, Q. The answer is A, because in an isolated system, the net charge is conserved. So the Q nu on both of these is going to be the same, exactly the same.